Hello everyone and welcome back to The Game You Can Win, But Cannot Play. This is episode 2, and it's probably going to be a little bit of a shorter episode this time, because rather than going into the topological games, we're just going to talk about topology and give the very bare bones, basic, minimum amount of knowledge you need about topology to understand the rest of the videos. If you've already taken a class on topology, which, as I've mentioned before, most people watching this video probably have, you can feel free to skip this video if you want. So I think it's only natural to begin this crash course on topology with just saying, what is topology? And basically, it's the mathematical study of the structure of geometric shapes. Now that's a bit of an abstract and vague definition, so let's make it more concrete with a little example. You may have heard the sort of saying that, to a topologist, a coffee cup and a donut are basically the same thing. Now, you might be wondering what that means. Well, it means that both shapes have basically the same structure. One hole in them. In the coffee cup's case, that hole is the handle. In the donut's case, that hole is the hole. What topology tries to do is it tries to take this intuition of, oh, these shapes have the same vague structure because they each have one hole, and they try to sort of rigorize that. Rigorize, is that a word? Anyway, they make it more rigorous, more mathematical. So a lot of the big things you hear about in topology, like manifolds, and spheres, and the Poincare conjecture, that's about stuff like that. However, today we're not going to get into all of that stuff, because it's very complicated and very abstract. We're just going to go with the sheer basics of topology, stuff you'd learn maybe the first 3 chapters of a given topology textbook. And to do that, we need to come up with an axiomatic foundation for topology. And where we start is with set theory. So let's begin with a little crash course, sort of a sub-crash course of our topology crash course on naive set theory. So a set, it's a collection of things. That's a very, again, vague and broad definition of a set, but again, this is naive set theory, so we're going to have to be super rigorous. And what we mean by a collection of things is literally we take a bunch of doodads, thingamabobs, thingamajigs, usually numbers, but they can really be anything, even like abstract variables or whatever, and we say, this set contains those things. So for instance, this set here contains the numbers 1, 2, and 3. We could say that 2 is an element of this set. This is what this symbol here means, is an element of. We could also, furthermore, we could say that 4 is not an element of this set, because 4 is not among the numbers 1, 2, 3. Another example of a set is this one, Q, which is to say the set of all rational numbers, all numbers that can be expressed as a fraction. So for instance, 22 over 7 is an element of Q. It is a rational number. However, pi is not an element of the set of rational numbers, because pi cannot be expressed as a fraction. And finally, as our final example, we have the empty set, the set that contains no things. No matter, what thing we put here, it is not an element of this set. Really, anything where you can say, oh, such and such is an element, or such and such is not an element of the set, that's a set. So then we have some operations and some terms related to sets that we need to talk about. Now these are, again, the very most basic things you can do with sets. So, X is a subset of Y if every element of X is also in Y. So, for instance, here we have set 1, 2, 3, and the set consisting just of 2. This is a subset of this set because 2 is in 1, 2, 3. Every element of this set is in this set. However, if we change it so that this is instead the set consisting of the numbers 2 and 4, then this is not a subset of this set, because 4 is in this set, but it is not in this set. Similarly, Q, the set of rational numbers we talked about earlier, is a subset of R, the set of real numbers. Real numbers being any number that is, all numbers, basically, whether rational or irrational. So pi is a real number, pi is not a rational number, but every rational number is a real number. You can see here I've made a little Venn diagram representation of x being a subset of y. These are maybe our points, and all the points in x are also in y. There may be points in y that are not in x, but who cares? Next, Next, we have the intersection. The intersection of two sets x and y is the set of every point that is in both sets, all of them. So, for instance, if we have 1, 2, 3, and 2, 4 as our two sets, their intersection, which we denote with this little horseshoe shape. It sort of looks like the letter N. You can remember that because it stands for intersection, is 2, because 2 is the only number that's in both sets. Similarly, here we have the interval from 2 to 5. This notation here means that 2 is in the interval, but 5 is not, along with the interval from 4 to 7. 4 is not in the interval, 7 is. So every point between 2 and 5, including 2, not including 5. Every point from 4 to 7, including 7, not including 4. That's what this notation means. Anyway, their intersection is the open interval from 4 to 5, because if you're inside the interval from 4 to 5, you're inside this interval, and you're inside this interval. So, intersection. Sort of the counterpart of the intersection is the union. Now, the union of two sets x and y is the set of every point that is in either set, that is in at least one of the two sets. So here, 1, 2, 3 union 2, 4 is 1, 2, 3, 4, because 1 is in at least one of these sets, 2 is in at least one of these sets. Doesn't matter that it's in both, it's in either set, it's in at least one. 3 is in at least one of these sets, and 4 is in either of these sets. Similarly, if we take the union of these two intervals, we see that it's the closed interval from 2 to 7. Anything in here is going to be in either this one or this one. Maybe both, but it's going to be in at least one. And as before, we denote the union with a little horseshoe shape, this time facing upward, like a letter U, because U stands for union. Now, one thing that's particularly neat about intersections and unions is that just as you can add multiple numbers together, you can go 1 plus 2 plus 3 and not just 1 plus 2, you can also take the intersection and union of multiple sets. And the way that works is that you just say, instead of, both sets, you say in all sets. If it's in the intersection of A, B, and C, then it's in all of A, B, and C. It's in A, it's in B, it's in C. Similarly, if it's in the union of A, B, and C, it's in at least one. You replace this either with at least one. So maybe it's in A, maybe it's in B, maybe it's in C, maybe it's in A and B, maybe it's in all of them. It's in at least one, though. And what's even cooler is that we can extend this to taking the union and intersection of an infinite number of sets. And there are the rules again. It has to be in all of them for it to be in the intersection, and it has to be in at least one of them for it to be in the union. So I've given some examples here to illustrate that kind of confusing notion. So let's say we have the infinite intersection of intervals of the form minus 1 over n to 1 over n, open intervals of course, where n is any natural number, that is, any counting number, 1, 2, 3, 4, 78, 520, I don't know. In this case, the intersection of all these intervals, the infinite intersection, is going to be just the set containing the number 0. And this may seem a little counterintuitive at first, okay? So sure, maybe it makes sense that the number 0 is in this intersection. 0 is going to be in every interval of this form. It's going to be a point that is in every set. But what about all the other numbers? Surely there's some other number that's in this set, right? Well, no. Because if you give me any number that you think might be in this set, for instance, maybe pi over a million, I can point you to a natural number n, maybe 1 million, where, oh, that pi over a million, that's not in the interval minus a million, minus 1 over a million to 1 over a million. It's not in that set, so it's not in all the sets here, so it's not in the intersection. Meanwhile, if we take the infinite union of every open interval of the form minus n to n, with once more n being any natural number, then we get that this just equals R, the set of all real numbers. And again, this is because if you give me any number, let's say 65 trillion and a half, I can give you any natural number, say 65 trillion and 1, where, oh, that number you gave me, 65 trillion and a half, is in the interval minus 65 trillion minus 65 trillion and 1 to 65 trillion and 1. It's in that open interval, so it's in at least one of these open intervals, so it's in these intervals' infinite union. Now the final sort of naive set theory operation / definition that I want to talk about is the set difference. And the set difference, it's basically x minus y. Every point that's in x, but is not in y. So here we have 1, 2, 3, set minus 2, that's, as you might expect, 1, 3. Every element in 1 is in x, but not in y. 3 is in x, not in y. 2 is in x, but it is in y, so it can't go in here. Similarly, half open interval from 2 to 5, half open interval from 4 to 7. Take the set minus there, we get the closed interval from 2 to 4. Every element in here is in x, but every element in here is not in this interval here. 4 isn't in here, 3 isn't in here, and so on. Alright, so we've talked about sets now. But topology isn't just the study of sets, it's the study of structure. So if we have a set, we need to figure out a way to give it some sort of structure. And the way we do that, it turns out, is via these things called open sets. And well, what is an open set? Well, to understand what one is, we kind of have to look at open intervals on R, and how we can extend those to an idea of open sets on R. R, once more, being the number line, the real numbers, just every rational and irrational number. So, if you recall, if we have a set like this, that is an interval from minus 1 to 1, every number between minus 1 and 1 is in here, like 0, 0.5, minus 0.5, etc. But that is open in that it does not contain its endpoints. So minus 1 is not in this set, 1 is not in this set. Then we call that interval open. Similarly, if the same interval does contain its endpoints, minus 1 and 1, then we say that that interval is closed. Alright, reasonable enough. But what if we want to talk about sets other than just intervals? Because there's not a whole lot you can do with intervals. Well, there are plenty of things you can do with intervals, but there are a lot of things you can't do. So let's say we have some arbitrary other set, subset of the real line, like this. The union of two intervals, the open interval from minus 1 to 1, and the open interval from 2 to 3. Now, do we think this set should be open or not? Well, it doesn't seem to contain any of its endpoints, because if we were to, sort of draw this out, we'd see, oh, well, if we had to choose what its endpoints were, we'd say they were here, 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 and here, and none of those are in the set. So it makes the most sense to say that this union of two open intervals makes, and hopefully I can write this upside down, an open set. Yeah, it looks okay. Alright, so maybe we can say that the union of open intervals, that's an open set. Open sets, when we take the union of open sets, we get open sets. Maybe you're cheating and looking over here and you see that that's the case. Alright, so now let's say we have the intersection of these two sets. The same interval. So the intersection of the open interval from -1 to 1 and the interval from 0 to 2. Well, the intersection of those sets, the set of all points that is within both of those sets, that's just another open interval. It's the open interval from 0 to 1. And, well, of course that's an open set. It's an open interval. Now, at this point, we might be tempted to say that just as the union of any open intervals are open, the intersection of any open intervals are open. But if we take that same good old infinite intersection again that we talked about just a few moments ago, well, if you remember, this is equal to just the set containing 0. And, well, what's the set what are the endpoints of the set containing 0? Well, 0, I guess, and, oh, it contains its endpoints, so I guess this, the most challenging yet of writing upside down, is not open. Luckily, there's a way to get around that, and again, if you cheated and looked on the right side of this board, you know what it is. We say that, okay, so maybe just the finite intersection, the intersection of, like, 2 things, 3 things, 4 things, stuff like that, that's open, but you can't do it infinitely like this. And if you're wondering what this entails for closed, well, it turns out to be pretty similar, except that it turns out to be infinite unions that you can't take. Any arbitrary intersection of closed intervals ends up being something that we might call a closed set because it contains its endpoints, but you can only take finite unions of closed sets. Now, there's one point about the terminology here I'd like to point out that's very confusing for people who haven't, really studied topology before, and even topologists kind of make fun of it. Whereas a door or a book can be either open or closed, not both, not either. Well, maybe both if it's like a jar or something, but whatever. Open and closed in topology, they aren't opposites at all. In fact, I've made this little chart here, open, not open, closed, not closed, to show that you can have sets that are of any combination of open and closedness. So, yes, so closed, not open. Well, okay, if we just have a closed interval, it's reasonable to say that it is closed and not open. And similarly, if we have an open interval, we can say that it is open and not closed. What if we have an interval like this, though? It contains one of its endpoints, but it doesn't contain the other. So you can't really call it open, and you can't really call it closed. Alright then, what about this quadrant here, though? What about open and closed? Now, it's a little complicated as to why, but it turns out that both R itself, that is, the set of all the real numbers, and the empty set are both open and closed, if we define it in the way that makes the most sense. Alright, so now that we've figured out what open and closed can probably kind of sort of mean in the set of real numbers, with the, with the standard way we would think about them being connected and open and having structure and yada yada yada, we can now try and extend that idea to any set X. Okay, so how do we get structure on X? Well, the same way we got structure on the real numbers. We figure out which sets on X were open. But if we have just an arbitrary generic set X that doesn't really have any intervals or stuff like that, how do we decide which sets are open or not? And the answer is, we just kind of decide. The same way that we decide that the square root of -1 is this new number I just made up called I. Because mathematicians can do that, and it often leads to great results. So, let's say that we have a set X. We can declare a topology on X, not the field of topology, a topology. And that's just a collection of subset of sets of X, and those are the sets that we're going to be calling open. Now, for T to be considered a valid topology, 4 conditions, 4 axioms, have to be satisfied. First, the empty set has to be open. X itself has to be an open subset of X as well. The unions of open sets have to be open, and whether those unions are finite or infinite. And finally, the finite intersections of open sets have to be open as well. But then how do we define closed sets? Well, simply put, closed sets are complements of open sets. Complement meaning just the set of all points that are not in that set, or the entire set minus that set. And if we give X a topology, then we call X a topological space. Alright, so there are just three more terms that I'd like to talk with you about topology that will come up later on in this video series. The first is subspace topology. So, if we have a set, and the set has a topology on it, so it's a topological space, and if we have a subset of that topological space, and we want to talk about that subset as if it were its own topological space, there's a very natural way to do that, and that is the subspace topology. So, if we have Y being a subset of the topological space X, then we can say, okay, a set in Y, a subset of Y, is open in the subspace topology on Y, if and only if we can write it as the intersection of an open set in X with Y itself. This definition is kind of confusing, when you first hear it, but it's actually pretty simple when you put it into practice. So if the interval from 0 to 1 is open on the standard topology on R, and at this point we should probably specify, which topology in R we're talking about, because you can put really any topology you want on R. So the standard topology, the one we talked about on R, it's open there. Then if we take, Q, the subset of rational numbers, we can put a subspace topology on it. And on that subspace, the intersection of the interval from 0 to 1 of that open interval with Q, so that is every rational number that is between 0 and 1, well, that's going to be an open set in that subspace topology. So it's pretty easy once you get the hang of it. And then the final two terms I want to talk about are the interior and the closure. The interior, as you see, it's the largest open subset of A, and the closure is the smallest closed set that A is a subset of. Now, again, these definitions may seem a little bit abstract, so I've drawn some pictures to help illustrate it. Because, intuitively, an open set is one that doesn't really contain its endpoints. It doesn't contain its boundary, if you want to be specific, and a closed set does contain its entire boundary. So if we have a set A and maybe it contains some of its boundary, maybe it doesn't, then the interior is just, A without its boundary. And then the closure is A with its whole boundary. Alright, so that's it for this video. Tune in for next time when we're going to talk about topological games. We're going to start actually doing the thing this is about. And Remember to like, comment, and subscribe. I don't actually care. I'm just doing this for a school project. I'm not planning on being a YouTuber. So yeah.